Hello everyone, and welcome to the first part of this talk on symmetries and instanton on special point manifold. So the goal of this part of the talk will be to describe certain very explicit examples of S1 invariant abelian G2 instantons. But before moving to the G2 setup, what I want to do first is I want to spend the first few minutes describing S1 invariant abelian instanton on hyperkähler 4 manifolds. And then what I'll do is I'll somehow repeat the analogous argument when the hyperkähler condition is replaced by the G2 one, and I'll try to build some sort of analogy and highlight the differences between the two sort of cases. Okay, so let me just get started. So here's our setup. We have a hyperkähler 4 manifold M4 with sigma 1, sigma 2, sigma 3 denoting the hyperkähler triple. So this is a symplectic form. Now, on a 4 manifold, a connection form A is said to be an instanton if its curvature form Fa is anti-self-dual. And equivalently, on a hyperkähler manifold, this means that the pairing between the curvature form and the symplectic form vanishes. Now, we are interested in S1 invariant hyperkähler manifold. So here's the setup. So we have an S1 action on our hyperkähler manifold, let's say generated by some vector field X. So X is a killing vector field, preserving the hyperkähler triple, so it's a triholomorphic killing vector field. Now, associated to this manifold is two pieces of data. So we can define a function V here, which is the inverse norm square of this killing vector field. And we can also define a connection form theta by the following expression here. And the function V here is S1 invariant, so it will descend to the quotient space, which I'm denoting here by U. It's essentially just R3. And using the hyperkähler moment map, we can define coordinates x1, x2, and x3 on the quotient space. And the whole hyperkähler data can now be expressed by the following expression here. Now, this function V and the connection form are related by the following relation here. So we see that if we differentiate the left-hand side, that the right-hand side has to vanish as well. So this means that the function V has to be harmonic. In fact, the Gibbons-Wolf-Gansat asserts that given a positive harmonic function on an open set in R3, one can define, by these expressions here, a hyperkähler metric. Now, we are interested in instanton on the spaces. So let's consider a connection form A on our hyperkähler 4 manifold, and we can express it in the following form here. So theta here is a connection form as before. Psi is a Higgs field, so it's a section of the endomorphism bundle associated to the gauge group we're interested in. And B here is going to be a connection form that is S1 invariant, so it descends to a connection form really on all three. In this case, the anti-self-dual connection condition becomes equivalent to the system of PDEs here. So V here is a harmonic function, psi the Higgs field, dB is the exterior covariant derivative defined on all three, and Hotstop with this note here denotes the Hotstop operator on all three itself. And this is the curvature of the connection form on all three. So this system of PDEs was studied by Kronheimer in his master's thesis, and this is usually called the Bogomolny equation. Okay, so the point of this construction is that the problem of constructing an instanton on a 4 manifold has been reduced to another problem, another system of PDEs on just a 3 manifold, which in this case is just R3. So it's somehow easier to tackle. And here's some immediate consequence of the Bogomolny equation. First, if you Hotstop both sides and you take the exterior covariant derivative, you see that the rescale Higgs field here has to be harmonic with respect to this connection form B here. So some simple consequence of this is that if the connection form B vanishes on R3, then to solve the system here, you just have to set your Higgs field to be the inverse of the function V here. And this corresponds to setting your connection form to be the dual of the killing vector field on the hyperkähler manifold. In other words, the curvature form is just the exterior derivative of this dual one form, and this belongs to the holomy algebra, which is SU2. So, for instance, for a hyperkähler 4 manifold, the group preserving the hyperkähler structure is, of course, SU2. This is generated by the multiplication by the imaginary quaternions, IJK. And here's a coordinate expression for the killing vector field. So there's 3 of them. So there's a 3-parameter family of ASD instanton that we can generate from this expression here. And these are indeed the usual anti-self-dual 2 form that you will get on R4. A here being some constant. So more generally, for any S1 invariant hypercube manifold, we see that the AST condition, at least for gauge group S1, is reduced to asking that this rescale Higgs field here is just the harmonic function on R3. And so in this way, we have determined all S1 invariant instanton on hypercube manifolds with triholomorphic S1 action. So for instance, this covers the multi-Rich-Hanson and multi-tubular spaces. Okay, so now our goal would be to repeat this sort of argument when instead of having holonomic group SU2, we have the holonomic group G2. Okay, so first thing I have to tell you now is what is a G2 instanton. So let's get to that. So in dimension 4, an instanton was a connection form A whose curvature belongs to SU2, which was the holomy algebra of a hypercube manifold. In higher dimension, for a special holomy manifold with holomy H, the connection form A is called an instanton if its curvature as a matrix of 2 form belongs to the holomy algebra H. So let us consider the case when the holomy group here is G2. So let me quickly remind you what a G2 manifold is. So given a 7 manifold M7, a G2 structure on the space is determined by an algebraic special free-form phi, so that at every point there exists some coordinate system in which the free form can be expressed in the following way here. So this is some one form dx1, and this guy here should be thought of as some sort of symplectic form on R6, and this term here is a real part of a Freezer form on R6, which is C3. So this free form determines both a metric and an orientation by the following expression here, x and y being arbitrary vector field. And such a data on a 7 manifold will define a G2 holomy metric if and only if the free form is covariantly constant with respect to the Lev-Schipper connection, or equivalently, the free form is both closed and co-closed. So in this context, a connection form A is said to be a G2 instanton if its curvature belongs to the holomy algebra, or equivalently, if the pairing between the curvature form and the dual 4 form vanishes, or we have this following sort of anti-Selldorf type condition. So this is very similar to what we saw in the hypercube case. So in the previous case, I used the Gibbons-Hall ansatz to describe S1 invariant hypercube manifold. So in the G2 case, we're interested in S1 invariant G2 manifold. So I need to describe what do the quotient of S1 invariant G2 manifolds look like. Okay, so here's our setup. We start with a G2 manifold M7 with the freeform phi, and we actually have a killing vector field X, which preserves the freeform. Then, as before, we can define a canonical Riemannian connection by this expression here, and we can define the inverse norm square of this killing vector field. Then, the freeform can be expressed in the following way. So you can define a non-degenerate 2 form omega by simply contracting the vector field X with your freeform, and similarly we can define a free-zero form by this expression here. Here's the real part, here's the imaginary part, and all this data being S1 invariant will descend to the quotient space, which I'm getting here by physics, and this will give an SU3 structure on the quotient space. So capital omega here is the free-zero form, omega here is a form of type 1,1. We have an almost complex structure J here, and G here is somehow the induced Riemannian connection on the quotient space. Now, in general, this data is not going to be torsion-free, i.e., it's not going to be Calabi-Yau freeform. In fact, what was shown in the work of Apostolf and Salmon was that the quotient space is always a symplectic manifold, so the 2 form is always closed. However, the Ninhai tensor of this almost complex structure J here doesn't vanish. In fact, it is essentially determined by the 1,1 part of the connection form theta here. Okay, so this guy here is a free-zero form, and the Ninhai tensor is essentially determined by the 2-2 component of the 6-0 derivative, which is exactly this term here. Okay, so let us now move on to the S1 invariant G2 instanton condition. Okay, now as before, we consider connection form A, which can be expressed in the following form here. So psi is going to be a Higgs field as before, and being S1 invariant, it's going to reduce, it's going to be a Higgs field on the quotient space, so on this manifold P6, and B here is going to be a connection one form on this space. Then the S1 invariant G2 standard condition can be rephrased in the following way. So we end up getting that the curvature form of the connection form B on our 6 manifold has to pair with the symplectic form to vanishes when the 2 form is contracted with it, and we get an analog to the so-called Bernoulli equation. So recall that this thing here is the exterior covariant derivative with respect to B. This equation here is, all this equation here is on P6. And on the right-hand side, we get the curvature of the connection form B, and it is paired with the real part of the free will form. So in the previous setup, we had a very similar expression in the Heidegger case, where this term here was essentially missing. In particular, if you Hodgson both sides and take the exterior covariant derivative, you apply it using the Bianchi identity, we see that this rescale Higgs field is no longer harmonic, but instead has to satisfy some sort of condition here related to the curvature of the connection form B and the curvature of the S1 action on our G2 manifold. So here's some simple consequence of the system of pairs. First, we see that if the Killing vector field has constant size 1, then this forces our G2 manifold to be a Riemannian product. So our manifold split as a product of S1 and the Calabi-Yau threefold P6. And this system of equation here reduces to what is known as a Calabi-Yau monopole equation. So this is a system of equation on Calabi-Yau threefold. For instance, this was studied in the work of Gonzalo Oliveira when the Calabi-Yau manifold was a cotangent bundle S3 with the Stenzel metric. And in addition, if we set, for instance, the Higgs field to be constant, then this system of equation just reduces to the so-called Hermitian-Yankees condition. Traceless because we need that the pairing between our curvature form and the symplectic form vanishes. As before, we see that if we set our connection form B here to be 0, to vanish on our 6 manifold, then we can solve the system here directly by setting psi to be the inverse of this, of the norm squared of our vector field. In other words, the connection form A is nothing more than the dual of the Killing vector field. So what we're saying is that if a vector field preserves a free form, then its dual, the exterior of its dual one form, in fact, belongs to the whole hadron. So it defines a G2 instanton. So for instance, on R7, the group preserving the G2 free form is a G2 itself, and this has dimension 14. So this will give you 14 such abelian instanton. So now one might wonder, well, what about non-trivial examples? So R7 has trivial holonomic group, such as the identity. So what about manifolds which have holonomic equal to G2? So here's a sort of simplest example. So we consider the spinor bundle of S3. So topologically, this is just S3 plus R4. And this is one of the first manifolds that was known to admit G2 holometric. This was shown in the work of Brandt and Salmon. So they showed that this manifold admits an SU2Q invariant G2 metric. And later on, it was showed by work of Brandhuber, Gomes, Gupster, and Gukov that in fact the Brand-Salmon metric belongs to one parameter family of SU2 squared times U1 invariant metric, so they have less symmetry. And this was rigorously proven by the work of Bogov and Skaya. Okay, so on S3 plus R4, there's a large family of G2 Horn metric. So in this case, the metric is actually equal to G. And these are converging to one type metric. So these groups act with principal orbit having codimension 1, generally speaking. In this case, the principal orbits are S3 plus S3, and the singular orbit is the 0 section of the spinor bundle, so just S3. So what our proposition says in this case is that there's a 9-parameter family of abelian G2 instanton on the Brand-Salmon space, because the isometric group, the group preserving the free form, is SU2Q, and this has dimension 9. Whereas for the BGG family, there's a 7-parameter family of abelian G2 instanton coming from the dimension of SU2 squared times U1. So previously, Jason Lerdier and Gonzalo Oliveira studied SU2 squared invariant instanton for these exact G2 metrics. And they found that for the Brand-Simon space, there's actually a free parameter family of abelian G instanton. And these indeed correspond just to the symmetry, because they were working in the SU2 square case, whereas the Brand-Simon metric has an extra SU2 symmetry. This difference, this extra free parameter family, was exactly coming to this extra sort of SU2 symmetry. So all the abelian instanton that they found in the SU2 square setting, in fact, was coming from the extra SU2 symmetry. Whereas for the BGG family, they showed that there's also a free parameter family of abelian instanton. And in this case, in this free parameter family, one of them was actually coming from this extra U1 symmetry. And another two parameter family was actually not coming from the symmetry. So this was sort of other type of S1 invariant G2 instantons. And there are plenty of other examples of combinatorial one examples of G2 metrics. For instance, there's the anti-cell job model S4, which has symmetry group SP2. So there's a 10 parameter family of abelian instanton in this case. And there's also the anti-cell job model CP2, which has instead symmetry group SP3. So there's an 8 parameter family of abelian G2 instanton. Okay, so now let me go back to the Apostol Simon construction. Now recall earlier I said that if we have a G2 manifold with an S1 action, then the cohesion space is going to be a symplectic manifold, so it has a closed 2 form. But in general, the induced SU3 structure is non-interval. In fact, the Nihai tensor of the associated almost complex structure is determined by the following expression here. Now, in the work of Apostol and Salomon, they consider the situation when this almost complex structure is in fact interval. And this happens if and only if, of course, this free zero form vanishes, in which case the 6 manifold is a Kähler manifold. Now, in general, it's not going to be a Calabi-Yau freefall. In fact, this 6 manifold is a Calabi-Yau freefall only if this function V here is constant. So V being constant is equivalent to saying that the S1 orbits have constant size. And in this case, our G2 manifold would split as a Riemannian product of S1 cross the Calabi-Yau freeform. So if this function V is not constant, then you can define, well, you can use a function T here, which is a square root of V, as a Hamiltonian function. And you can define a Hamiltonian vector field. So just define a vector field xt here by the following expression. Now, so this naturally, of course, preserves the symplectic form, but it turns out that in addition to that, it also preserves the complex structure and hence also the metric. So this is a killing Hamiltonian vector field. So in such a situation, we can naturally take the Kähler reduction of our 6 manifold down to a 4 manifold, which I'm denoting here by Q4. So Q4 is going to be a complex manifold, and it turns out that it inherits a holomorphic Q0 form, which I'm denoting here by omega 2 plus I omega 3. So this is due to the fact that on our 6 manifold, we had a holomorphic 3-0 form. And now, depending on the choice of for the moment map, so we have a moment map T, and we can take different values of the level set to perform the S1 reduction, so get different Kähler form. So we end up getting a 1 parameter family of Kähler forms on our cohesion space. Now, there's 2 pieces of data that we can associate on that we can define on our 6 manifold. Namely, there is the inverse norm square of our Hamiltonian vector field, and there is a canonical Riemannian connection. So this is the same sort of formulae that we use to define the connection from theta and function V from early on. Now, all this data is going to be invariant under this killing vector, is this Hamiltonian killing vector field. So it's going to define the data on our 4 manifold. In other words, the problem of finding G2 metric on our G2, the 7 manifold, can actually be rephrased as a system of PDs purely in terms of the 4 manifold Q4 here, which is a complex manifold. So the formal statement is given as follows. So this is the Apostol Simon construction. Given a complex 4 manifold Q4 with vanishing first joint clause, so holomorphic 2-0 form omega 2 plus omega 3, if on this manifold we have a 1 parameter family of Kähler forms omega 1 twiddle and a family of positive function ut here, satisfying the 2 conditions below. So the first one here is a second order PD relating the symplectic form, the Kähler form, to this function u here. And the second one here is an algebraic relation between these 2 objects. here the Q is exterior derivative of on the 4 manifold, and DCQ is just J, the complex structure on this complex manifold Q composed with D Q. Okay. If you can solve this pair of PDs, then you can define a 7 manifold M4 to be, well, locally it is a T2 bundle over our complex manifold Q4, and you can cross that with essentially an interval. Now this T2 bundle is determined by the following curvature condition here. So it's a T2 bundle over Q determined by these two conditions. And on this 7 manifold, you can define a torsion-free G2 structure by this two expression here. So this produces a torsion-free G2 metric on our 7 manifold starting from this data on Q4. So this naturally motivates the search for T2 invariant G2 instantons on the Hausdorff Salmon space. So what we should expect is that we should expect that one should be able to rephrase the G2 instanton condition in terms of a system of PD on the complex 4 manifold Q4. So here's a proposition. Suppose we have a G2 instanton A of the following form. So psi and chi here are Higgs field on the 4 manifold Q4, depending on T. So these are sections of the endomorphism bundle associated to the gauge group. And B here is a family of connection form on Q. And then this connection form A here defines a G2 instanton if and only if the following system of PD here holds. So let me tell you what's what. So this is a Lie bracket between the two Higgs field chi and psi. FBQ here is a curvature of the connection form B on Q. And the operator I2 here is an almost complex structure associated to this data, to this complex and scalar data on this 4 manifold Q4 here. I'm not going to be very accurate about that because it will depend somehow on the scalar structure. So it depends. It's an almost complex. It's a complex structure that depends on this scalar form. So and dB here is the exterior covariant derivative on Q associated to the connection form B here. So let me just make a quick sort of dimensional count of the system of equations that we are currently considering. So recall that the G2 instanton condition consists of 7 PDs. This is 7 PDs, well, times the dimension of the gauge group. And in this case, this is 1 PD here. This is a PD involving 1 forms on our 4 manifold. So really this corresponds to 4 condition. And there's this 2 system of PDs here, which corresponds to, again, 2 condition here. So the dimensional count shows that this indeed corresponds to 7. Okay, so this is a consistent. We're not missing any equation. Now, in principle, solving the system of PDs is rather hard. One thing I should say is that one way of thinking about this equation is somehow as a Hitchin type equation. You should think of it as a Hitchin type equation for a G2 manifold. So the Hitchin equation, strictly speaking, occurs when you do a T2 reduction of the anti-central condition on a 4 manifold. So early on, if we do an additional S1 reduction of the Bernoulli equation, then we get this Hitchin type equation. So in our setting, we're doing somehow a T2 reduction of a G2 manifold. So this is somehow the analog that we get. Now, Apostolov and Simon showed that the system of PDs can be solved in the simplest sort of situation when the 4 manifold is just a hyperkähler manifold. So if Q4 here is a hyperkähler manifold with hyperkähler triple sigma 1, sigma 2, sigma 3, and if in addition to that we have the data of a closed antisocial 2 form, then we can solve this pair of systems. This automatically solves the system here, and we get a torsion-free G2 structure. And the solutions given by these two sort of, this is the family of positive function that you get, and this is a family of scalar forms. This all depends on 4 constant P, Q, R, and S. And the T2 bundle over our 4 manifold is determined by the following 2 curvature forms. In the case of abelian instantons, so when the when the gauge group here is S1, and if we just set the connection form on our hyperkähler manifold to just be 0, then all the system reduces to a single sort of condition here involving this rescale Higgs-field chi. And we can very easily solve the system in the following setup here. So the simplest example of a hyperkähler manifold is just R4. So just take flat hyperkähler structure on R4 and set the constant to be mostly 0 except Q, which we're going to set Q here to be 1. Then very concretely, you can actually define the connection forms in local coordinates. Here's the expression, and the G2 metric takes the following form here. So this metric here, you can check that it has holonomy equal to G2. However, this metric is not complete because this function here, this coefficient function here, is going to blow up by T0. But as T goes to infinity, this metric is indeed complete. So this is a holonomy G2 metric, and we can construct lots of abelian G2 instanton on the spaces. So here's some examples. Here's the first one here corresponds to the dual of the killing vector field associated to X and XT. Because these are killing vector fields which preserve the G2 freeform, these naturally define G2 instanton. But actually, there are other abelian G2 instanton which do not come from any sort of symmetry. So you can check that these indeed solve this system here. And more generally, if we choose any constant, PQRS, then we can easily solve the system again. Well, it's a bit trickier, but you can still solve the system and you find the following families of G2 instanton. So what we're saying here is that this PQRS will not only parameterize a family of G2 metrics by the subsample construction, but also we can also define a family of G2 instanton depending on this constant PQRS. Okay, so in the next talk, I will somehow describe a similar sort of situation when the G2 manifold is replaced by spin 7-1. And I'm going to argue that essentially everything I said today can actually be extended to the spin 7 setting. Thank you.